Winter storms are common in Southern California, especially during the cooler months. However, on January 22nd, 2024, San Diego County experienced an unusually severe flash flooding event. This flooding was caused by a winter storm system that included a weak atmospheric river, classified as AR0, along with a low-pressure system over Southern California. What made this event unusual is that despite the atmospheric river being relatively weak, rainfall intensity was extreme and highly localized over San Diego. This raises an important question. How did such a weak atmospheric river produce rainfall intense enough to cause record-setting flooding and widespread damage?
At its peak, the rainfall from the January 22nd storm reached 1.5 inches per hour, an intense rate for Southern California. January temperatures were slightly above the 20th century averages, which can influence soil moisture and storm behavior. The flooding had significant impacts on local communities. In San Diego alone, over 1,200 residents were displaced and multiple homes and streets were flooded. Across the broader region, thousands of structures were damaged and landslides and rockslides were triggered by the excess water. Several background factors made the flooding worse. Storm drains were clogged and aging infrastructure struggled to handle the concentrated rainfall. City leaders have noted that extreme weather, fueled in part by climate change, is becoming increasingly common, highlighting the need for resilient urban planning and improved stormwater management.
The first variable in this storm was sea level pressure. On January 22nd, 2024, a low-pressure system sat over Southern California. Low pressure encourages air to rise, which leads to cloud formation and precipitation. At the same time, a weak atmospheric river, classified as AR0, moved across Southern California. Normally, this would produce light to moderate rain, but in this case, strong, low-level moisture flux and mesoscale forcing beneath an upper-level jet concentrated rainfall over San Diego. Even though the atmospheric river itself was weak, the combination of low-pressure dynamics and mesoscale jet forcing helped intensify rainfall, setting the stage for record-setting flooding. But it wasn't just the low pressure itself. The surrounding pressure gradients created strong winds that pushed air upwards continuously, sustaining heavy cloud formation and rainfall over several hours. Mesoscale jet streams in the upper atmosphere enhanced this upward motion locally, concentrating rain over San Diego rather than spreading it evenly across Southern California. In short, the combination of the weak atmospheric river, the low pressure system, steep pressure gradients, and mesoscale forcing turned what could have been a normal winter storm into an intense, short-lived rainfall event. This set the perfect conditions for flooding. Next, let's take a look at precipitation. On January 22nd, 2024, San Diego Lindbergh Field recorded 2.73 inches of rain, setting a new daily record. The previous record, from 1963, was 1.57 inches, so this storm more than exceeded historical extremes. The rolling 3-hour precipitation peaked at 2.13 inches, which corresponds to a 178-year interval, meaning there's only about a 0.6% chance of this happening in any given year. In other words, this was an exceptionally rare event. Flood risk increased when rainfall is both intense and concentrated over a short time, even if regional tools aren't extremely high. Southeastern neighborhoods in San Diego were underwater within hours, displacing over 1,200 households and stretching emergency services to their limits. Urban surfaces made matters worse. Saturated soils, impermeable pavement, and clogged drains prevented water from draining quickly. Even though the atmospheric river was classified as weak, these factors combined to create catastrophic flooding in parts of the city. Now that we've seen how rainfall accumulated, let's examine the impact soil moisture and the city's infrastructure had on the flooding severity.
To understand why the flooding was so severe, it's important to look beyond rainfall and consider ground conditions and urban infrastructure. In the weeks leading up to January 22nd, several rain events left soils already moist, reducing their ability to absorb additional water. When intense rainfall occurred, much of it became surface runoff rather than soaking into the ground. Urban development further amplified this effect as roads and buildings create impermeable surfaces that direct water into storm drains and flood control channels. However, San Diego's drainage infrastructure is aging and limited in capacity, and debris buildup in channels reduced their ability to carry water efficiently. As a result, intense short-duration rainfall quickly overwhelmed the system, leading to widespread flooding. These variables were selected because each represents a key part of the flooding process. Sea level pressure helps explain the atmospheric setup and why air was forced upward, allowing storms to intensify. Precipitation captures the immediate trigger intense, short-duration rainfall that overwhelmed the landscape. Soil moisture and urban infrastructure explain why that rainfall turned into flooding. Saturated soils reduced infiltration, while impermeable surfaces and limited drainage increased runoff. Together, these variables show how a weak atmospheric river, when combined with favorable atmospheric dynamics and vulnerable urban conditions, produce severe flash flooding in San Diego.
The January 22, 2024 San Diego flood demonstrates how extreme impacts can result from the interaction of multiple atmospheric and environmental factors. Although the atmospheric river associated with the storm was classified as weak, low-pressure dynamics and mesoscale jet forcing enhanced upward motion and concentrated rainfall over the region. That rain fell over a short period, quickly exceeding infiltration capacity. Saturated soils, impermeable urban surfaces, and limitations in stormwater infrastructure further amplified runoff, leading to severe flash flooding. This event highlights the importance of examining not just individual weather variables, but how atmospheric processes, land conditions, and urban systems interact to produce extreme outcomes. As intense rainfall events become more frequent, understanding these combined processes will be critical for improving flood preparedness and resilience in urban areas such as San Diego.